Welcome everyone for the first tech talk of the year. Uh, uh, so we have William Moses from MIT giving a talk on enzyme, high performance differentiation mechanism for LLVM. William is a graduate student at MIT and he works on compiler and related areas. And much of the work he's doing, not just this one, but other things, is of great interest to NVIDIA. So with that, I'm very happy to have him come here and tell us about Enzyme. Please take it away.
Fantastic. So first of all, if you have questions at any point, feel free to immediately chime in. I don't actually see a live chat window, so feel free to say it. Cool. And yeah, as mentioned, I'll be talking about Enzyme, which is a tool for being able to take arbitrary LLVM code and perform automatic differentiation on it. And this work is not just the work of myself, but a large team composing folks from MIT, TUM, Argonne National Lab, and beyond. So to begin, we're going to talk about everybody's favorite subject in high school or college, AP Calculus. So as a quick refresher, derivatives, they're able to compute the rate of change of a given function's output with respect to its input. And this is useful for a wide variety of applications across science, including machine learning, the backpropagation algorithm you can think of as a subset of differentiation, Bayesian inference updates, uncertainty quantification. Moreover, anything involving scientific computing, especially modeling or simulation. If you've ever seen a physics equation, it's almost certainly a differential equation, which inherently involves the use of derivatives. You can also borrow the notion of derivatives for a bunch of other completely unrelated applications, such as being able to determine where a floating point error occurs, where you have like a large floating point number plus a small number where the small number doesn't get accumulated into it. What's really cool is you can build a program that takes another program's function and then generates you the derivative of that function automatically. So for example, we have this code here on the left, this ReLU3, which says if x is greater than 3 or x is greater than 0, return x cubed, otherwise return 0. And we can run a program transformation to get the corresponding gradient of this function, which instead of returning x cubed, returns 3x squared at the corresponding location. And specifically, unlike numerical approaches for computing all the derivatives, the automatic differentiation process has two key benefits. First of all, it's able to compute the derivative of either all inputs or all outputs immediately in a single call. And specifically, it's also able to do so without having additional approximation error. So for example, suppose we had some function that took in a variety of inputs, say like 100 inputs, and we wanted to do this numerically. On the left, we'd have to do this for loop over all of the possible inputs to get the derivatives for all of those inputs. Moreover, we'd have to do this, plus epsilon, divide by epsilon, which introduces some amount of error in it. In contrast with the automatic differentiation approach, we can just call it one time, get the derivative of all the inputs without that error immediately inside of our gradient input array. There exists currently three approaches for doing so. The first approach is to say, okay, this is a somewhat hard problem to do on arbitrary code. Let's make a completely new language where every single operation inside of this language is explicitly defined to be differentiable. This requires taking your original program and rewriting it in the DSL. And moreover, that DSL must support every single operation from your original program. So for example, we take this ReLU3 example we had before, and we rewrite it in TensorFlow. Looks a little bit nasty, but it's still equivalent. We have the equivalent of the lazy evaluation of the if and the else pieces here with the lambda to the TensorFlow math.pow and so on. However, if the DSL doesn't have a good match that exactly represents the type of operation that you want to do, this can end up being a large performance debt because you have to effectively retranslate your reasonable code into some higher level operations that effectively match the functionality. In contrast, if your DSL exactly matches the type of operations that are available in your original program, it can be reasonably efficient. The second approach, which aims to be able to allow you to use this on more arbitrary code, is known as operator overloading. Examples of this include, say, adept in C++ or JAX in TensorFlow or in Python. And the goal here is rather than having an entirely new language, we'll define differentiable versions of specific language constructs. So for the C++ case, rather than having a regular double you compute with, you have this differentiable A double. In the Python case, rather than having your numpy.sum to work with data, you use your jax.sum. And then if you rewrite your program still now in that original language to use these differentiable language constructs, you can go ahead and compute the derivative. So if we wanted to use, say, the C++ version, I might rewrite my code here on the left to take in a template that lets it use any arbitrary type, be it the regular double or the differentiable double. Then again, on the right, I set up the computation that I want to do. So I say, oh, I have this instruction stack. So the way that these AD approaches inside of operator overloading tend to work is on the differentiable language construct, they'll go and store every instruction that's run for the original program into some instruction stack, as exemplified right here. And then when it wants to go compute the gradient, it'll, in reverse order, interpret every operation on that instruction stack, allowing you to go ahead and compute the end value of the derivative. Now, the problem with this is that this instruction stack is often dynamic. Then this means that you have to effectively interpret inside of a large for loop with a switch statement over all the types of instructions, the program that you originally ran, which is not great for performance. Moreover, even though we're a little bit closer to the original program that you have right now, you're still likely to have to rewrite your code to use some non-standard utilities. And the reason for this is that these existing language constructs don't cover the entirety of the language. So for example, in the NumPy case, if you have any code that isn't written in NumPy and just uses regular Python or say calls a Python library, then you're kind of out of luck and you cannot use this tool. Moreover, JAX doesn't support all of the different types of NumPy constructs. And the same issues apply also with, say, the C++ example, where not everything is built to handle this special A double as opposed to the regular double, or there may not be a math function like sine. Sine is handled with this particular tool called adept, but some esoteric Bessel function might not have a operator overload for this, at which point you have to manually write the derivative again. The third approach sort of tries to combine some of the nice pieces from the other two and even go a little bit further. So this is called source rewriting, and the goal here is to say, rather than have people rewrite their program in a differentiable language, let's make that original language effectively fully differentiable. So it will take in as input the source code to the original program and the source code for any of the dependencies, such as any header files, etc., that you might have, run it through a tool that at the source level analyzes it and spits out new source, which will do the total computation. Now, this is useful because you don't really have to rewrite much code at all. But because you don't have to rewrite this code, the tool on the inside has to re-implement all of the parsing and semantics of the given language that you want to differentiate through. Moreover, because it's able to output directly the code rather than this sort of instruction stack that's later interpreted, it's able to be quite efficient. But again, because here it has to have all of this code to be able to take the original versions and spit out these differentiable versions, any dependencies that you might have or in any way involved with the computation you're doing have to be available completely ahead of time and passed into this tool. As a consequence of this, the source rewriting approach tends to be quite efficient, but it also tends to be quite fragile, because if this tool has to implement the parsing semantics of the entire language, then any slight modifications to the language or higher level constructs end up not being handled. So in this case, this tool called Tapenade only handles a very specific subset of C code. And that's because all the higher level constructs, especially any C++, are too complex for it to understand and thus create new versions of. Regardless of which of those three approaches you go through, they all tend to follow the same overall pipeline. You have your source code in your original language, you run some differentiation procedure on top of it, and you end up with new code in that language. It could be a modification of it or just completely new code that's spit out. And you have a tool specific to the language that you want to differentiate. Then regardless of the procedure that you got there from, they go through the traditional compiler pipeline where we lower it to some intermediate representation, we do a host of optimizations on top of it to try to make it fast, and then we output an executable that we eventually run. So let's see how this general pipeline used by all those existing tools works in practice. So here I have two example functions. So I have this normalize function that takes an input vector and an output vector, and then computes the normalized version of this vector, saying the output equals the input divided by the magnitude. And since the magnitude function is itself computed in O of n time and specifically computed inside this loop, the normalized function itself will be computed in O of n squared time. Now, any good compiler worth its salt will realize that the call to that magnitude function inside the loop can be hoisted out the loop, reducing the runtime of the normalized function from O of n now down to simply O of n, an asymptotic performance boost. Now, if we were able to do that optimization first, now remember, all of those existing tools have to first run differentiation prior to optimization, we end up with the magnitude outside the loop. And the differentiation procedure here effectively takes all of the instructions in your original program and runs a modified version of them backwards to compute the derivative. So because we had this magnitude function outside the loop in the optimized code, when we differentiate it, we have the gradient magnitude function on the outside of the loop in the derivative code. So now let's take a look at how those existing tools might work on it. So again, remember that we need to run differentiation before optimization for all of these existing tools. So first we have the magnitude function inside the loop, that's at O of n squared. Doing the derivative, just reversing this, keeps the gradient magnitude again inside the loop, having our gradient be run in O of n squared. But now when we try to do that same loop optimization, we can't do it. And the reason why is because this gradient magnitude function uses a variable defined within the loop, this dres variable, which prevents it from being hoisted outside, keeping us at the slower O of n squared time. And the real moral of this story here is that if you're able to instead differentiate after optimization, you're able to create asymptotically faster gradients. So that's exactly what our tool Enzyme is designed to be able to do. So by pushing the differentiation procedure down inside the low or LLVM level, we're able to now work on optimized code. Moreover, additionally, because the LLVM level is able to be the intermediate representation for optimization for all of these different languages, we can, with a single tool, differentiate code independent of what language it comes from, and moreover, independent of what new language constructs may have come into play. So you might ask why we specifically chose to do this on the LLVM level, and there's a couple of key benefits that this provides us. Specifically, is as a generic low-level compiler infrastructure, it has a variety of front ends, and at this point, most of the languages, be it C, Rust, Fortran, Swift, Julia, all go down to LLVM at one point. Here us to differentiate through all of the things built out of it. Moreover, it also has a variety of different it goes to CPU, it goes to RISC-V, it goes to NVIDIA, and so on. It also has very well-defined semantics for every instruction, as well as a suite of different optimization passes and an analysis path that we can build on top of for our AD tool. So let's take a look how in practice the differentiation procedure would work on the LLVM level. So let's take that same example we've been talking about, the C code here for ReLU3, and we wanted to use Enzyme, specifically the C sort of front end for Enzyme or C++ front end. We would call the derivative by first calling this magic function Enzyme AutoDiff, passing as the first argument the function that we wanted to go ahead and differentiate, and then pass any additional arguments that are necessary for the function or its derivative. At the LLVM level, that original C code is represented as a series of instructions that are themselves inside of a control flow graph, hence these nodes and these edges representing the different way that the computation can propagate forward. So specifically here, we have the conditional check if x is greater than 0. If so, we will compute the call to POW, and regardless, we will merge the two results of either not coming from that branch or coming from that branch and return the result. The first thing that Enzyme does is it deduces what all of the active instructions and values may be for the program. Now, specifically, activity in this sense is defined to be whether or not a given instruction or given value can impact the computation of the derivative. This is really useful because in practice, it allows us to say, hey, this part of the computation doesn't impact the derivative, thus we don't need to compute the derivative of it. An example of this might be, say, you have two inputs and you only care about one of the derivatives as an output, and that recursively throughout the entire program. Moreover, it also allows us to avoid taking the derivative of anything that's ill-defined. So if you, say, have a CPU ID or get thread number instruction, it isn't meaningful to ask for the derivative of those functions, and thus, as a consequence, we don't need to if we run this activity analysis first. That for all of the values that we deduced were active, in other words, that are important for the computation of the derivative, we're going to go ahead and allocate and zero shadow memory for those active values. Now, what the shadow memory represents is just an equivalent memory location for which we're going to store the gradient of that value. The reason we start by zeroing it is because we increment them by the partial derivatives of any subsequent uses as we see them. Then we go ahead and we insert a reversed version of that original control flow graph and compute for every active instruction what the corresponding derivative propagation would be for it. So as an example, if we take that x cubed instruction we saw before, the corresponding way to propagate the derivative is to increment the partial derivative of its input by 3x squared. Now, if we were to optimize that entire program of the original and the derivative together, we get something that looks quite simple. It's just effectively if x is greater than 0, return 3x squared, which if we rewrite this now inside of, say, C, we get something that looks exactly like that optimal handwritten derivative. Now, of course, doing this at a low level hadn't been done before, and for good reason. The historical belief was that doing it at a low level lacked the information that was required to compute derivatives, and that you could only do it if you had all of the high-level information. A quick example of this right here, suppose we have, and now just a purely C example, a call to the memcopy function, which copied 8 bytes from some source pointer to some destination pointer. Now, the corresponding derivative of this function is going to be different depending on what the type of those pointers data actually is. So if this memcopy really copied 8 bytes of a single 64-bit double, the corresponding reverse pass to compute the derivative would be to do one 8-byte floating point add. In contrast, however, if instead this represented 2 4-byte floats, the corresponding reverse pass would be having to do 2 4-byte floating point adds. And unfortunately, as the one 64-bit add is not equivalent to 2 32-bit adds, you would get the wrong result if you chose the wrong derivative copy. Now, the way that Enzyme remedies this is we provide a new interprocedural data flow analysis that's able to detect the underlying type of all of the data. So specifically, we define for every value in our program a corresponding type tree that says that at this set of memory offsets, it will have this given type. And we perform a series of fixed point updates throughout the instructions to deduce for all of the values that we need the type of the underlying data. So as an example, suppose we had here a struct myType, which contained first a double, then a pointer to an int, and we had a pointer to this myType. The corresponding type tree for x would be at byte offset 0 a pointer, which itself contained at byte offset 0 that double, then another pointer, now to an integer. Now that we've demonstrated all the tools we need to be able to make differentiation work at the low level, the natural question is how well does this work in practice? So we took a collection of benchmarks from the standard AD benchmark suite from Microsoft and a couple of others of technical and scientific interest. And then we performed a comparison where we first had Enzyme in the location that it should be run at, which is after optimization. And we compared it with an equivalent version of itself where we first ran it before any optimization and then ran 2 rounds of optimization afterwards. And the reason we did this is because, with the exception of Enzyme, all other tools have to run before any optimization process. So this really let us get an effective ablation analysis, because there might be some minor differences in implementation between Enzyme and, say, another tool. We also took the 2 fastest tools that had been benchmarked, Topinot, which is a source rewriting tool, and Adept, which is an operator overloading tool. And specifically for all the tools where we aren't able to run optimizations first, we run 2 rounds of optimizations after the fact. And the reason why is because some optimizations in LLVM may not be idempotent, and thus, if you run everything twice, then you keep a consistent way of getting all the results. It turns out for these benchmarks, they are, and it doesn't make a difference to run it a second time, but just for consistency's sake, we did. So one can now see inside of this graph exactly how Enzyme stacks up and how we can test that hypothesis that running optimization after running differentiation after optimization is able to hold up. So here we take all of our benchmarks and we plotted the relative speed up of the differentiated function on those benchmarks. In essence, higher being better. So the first thing to look at is the difference between Enzyme and the reference pipeline here, because that shows how much being able to run optimizations first may matter. And for a variety of these applications, if you look at LSTM, bundle analysis, GMM, Euler, RK4, you get a sizable speed up. Some of these other benchmarks, such as the FFT test and the Brussels Rater test, didn't see that much of a speed up. And the reason for this is because those were already very highly optimized codes. Doing any optimizations, even on the LLVM level, didn't produce a different program, thus why you get similar performance. But if you take the geometric mean overall of all of these programs, we see that there's a 4.2x speed up simply by first being able to apply optimization, no other difference in the insides of the tool. Now, it's also interesting to look at how Enzyme's able to stack up against the state-of-the-art tools regardless. So if we look at, for example, the LSTM and bundle analysis case, we see that the reference pipeline is very similar in performance to Topinot, and thus we can conclude that the reason that Enzyme overall is able to get a speed up above Topinot probably is because we're able to run those optimizations first. Now, this isn't necessarily the case here across the board, and the reason for this is because there are differences in the underlying implementation of how these tools represent and then store the instructions. As an example, Topinot or Adept tends to do more poorly across these benchmarks than most tools, and the reason for this is because Adept has to store that instruction stack of tape and then thus reinterpret to compute the derivative all of these pieces. A couple of other things of note, there's an X here for Topinot on both the Euler and RK4 tests, and the reason for this is that these are both C++ tests that heavily use the ODEINT library inside of Boost, and Topinot cannot deal with any C++ code, being a source rewriting tool. We also provide, since we're able to differentiate arbitrary code and these arbitrary languages, some nice example frontends how you could use this inside of a higher level tool, such as PyTorch or TensorFlow, as a generic foreign function interface in essence. So suppose you have some climate or ocean model in an external code base written in Fortran or C or something that isn't already written in PyTorch or TensorFlow, you can use Enzyme to compute the derivative of that code base and thus integrate it directly into your deep learning model and then still use it for computation. The next big question here is how we can get this to work on GPUs. Now, prior work has not been successful in exploring reverse mode differentiation of existing GPU kernels, and that's for 3 different reasons. The first reason is generic parallelism, regardless if it's GPU parallelism, CPU parallelism, or whatever else. When you do that reversal process, it can lead to data races, which lead to incorrect results. The second reason is that the complex performance characteristics of the GPU itself make it difficult to synthesize efficient code, and moreover, specific resource limitations on the GPU can also prevent kernels from running at all. Happily, we're able to, through various methods that I'll immediately describe, resolve these 3 issues, making us the first tool to take generic GPU kernels and perform reverse mode automatic differentiation on them. So before we talk about GPU-specific parallelism, let's do a slightly easier version with just generic parallelism. So suppose we have just a parallel for loop here on the left, where we set the output of a given array at all indices equal to some value. Now, we read for all iterations of this loop the same value val, and that's completely safe and completely fine here, no undefined behavior. However, when we reverse the original program to compute the derivative in the reverse pass, all your reads turn into writes and vice versa. So whereas we had these concurrent reads here on the left, we have concurrent writes now on the right, leading to a write race to accumulate the different partial derivatives of dval. And since you have simultaneous writes in a parallel for loop, you'll potentially get the wrong answer. The second of these problems that I mentioned, which hopefully being NVIDIA comes home to a lot of the stuff you guys design, is we can talk about the GPU memory hierarchy. So at a broad level, there's three types of memory that people tend to care about. This is per thread memory. In essence, these are most commonly seen as using registers. It's on the order of bytes. If you use too many of these, it'll limit your parallelism, but it's by far the fastest thing. And if you can use registers, you should. The second level here is a type of memory that's usable and shared between different threads within a block. Shared memory, it's more on the order of kilobytes. So you got more of it if you need, as opposed to the registers. Also, if you use too much of it, it'll limit the amount of parallelism you have. Not quite necessarily as fast as a register, but still reasonably efficient. And then finally, we have global memory. This is per GPU. You can use it anywhere. There's a lot more of it. Tends to be on the order of gigabytes, especially on the newer cards that you have coming out, but it's very slow. And the way that we resolve the race problem is, and also the way that we resolve that memory hierarchy problem, is actually to think about them together. So specifically, the goal here is, can we resolve races in a way that matches the same performance characteristics as the memory that they were racing on originally? And the reason why this is useful is if you had very, very fast code, because it used all the very fast types of memory to begin with, we need to ensure we have a very, very fast derivative. So then the overall program has a similar behavior. However, in contrast, if you had some slow code to begin with, say it was all this small part of your section of your program was using global memory, it's okay on the derivative of that part of your program to fall back to a slightly slower version. And if you do this for the entire thing, you'll end up with a similar performance characteristics for your derivative as you had for your original program. So specifically for the thread local memory part, we can resolve this in the accumulation by just doing a regular non-atomic low and store. Now, this is the fastest possible memory you could have to begin with, and thus the fastest possible derivative computation you could have. Say you had the same memory location across all threads. Examples include some types of shared memory, but this can also potentially be more general. The way we can resolve the races here is to just do a parallel reduction into the variable. And finally, that fallback, which is a catch-all for everything else, where you don't have any information about the type of memory, you can just do an atomic add and preserve correctness. The last big thing about the GPUs, in addition to having those different types of memory and the parallelism, there also exists specific synchronization primitives which allow you to maintain certain characteristics of your program. And here it's specifically defined where you have some code which is run, and then you have your sync threads and some code that's run afterwards. The sync threads, in essence, guarantees that all versions of your first code, your code A, run before your code B. Now, it turns out the sync threads is only necessary if A and B could potentially access the same memory, and thus what we're able to show is if your original program was race-free, if you perform a sync at the corresponding location in the reverse pass, you're able to preserve correctness of your gradient computation. And we do so by proving correctness by cases, and I'll show you one of these cases as an example. So suppose inside of your first code, you store into some pointer, you sync, and then you potentially load from that same pointer. The corresponding derivative computations that would be generated for that in the derivative code B case would be the atomic add into the derivative pointer. And again, we could do the slightly faster versions as we showed earlier if we prove that it's better memory, but for now we can just assume that it's a regular atomic add. We do the sync at the corresponding location in the verse, and then the derivative of the store is to load the current value, use it for some subsequent computation going up, and then store it equal to 0. And here this is correct because all of the atomic adds onto D pointer must have been completed before we need it for use in this load right here. And this is guaranteed because of the corresponding sync threads in the reverse. We can now build an overall example. So for instance, here I have a simple CUDA code. So here I have this device function inner, which for all threads sets y of that thread equal to a times x at that corresponding thread. If we wanted to call it and get the derivative using enzyme, I would now call enzyme autodiff, except now inside of this global function, pass in the device function that I wanted to differentiate, as well as the corresponding values I need to compute the derivative. And here we have both the original inputs, a, x, and y, as well as the shadow inputs, dA, dx, and dy, and these dA, dx, and dy are where the gradient results are going to be stored into. Now, running the autodiff procedure on top of this will generate corresponding LLVM to it, but for ease of reading through it, I wrote what an equivalent version of this at, say, a C++ level would look like here on the right. So the corresponding derivative inner would first run the original program, often referred to here as the forward pass, and then run the gradient computation reverse pass here. So what it would effectively do is do the derivative of that store, which loads that value dy and sets it to 0. Then we propagate this value up into its operands, which here it would propagate into x, that dy times a of 0, and we would increment that into dx. And similarly, if we want to compute the derivative of a, we would do the same thing for the other location. Again, if we didn't know anything about those pointer types, we would have to fall back to an atomic. But it turns out we can probably analyze those pointer types to get some more information. So as an example, if we knew this here was unique per index, since it's unique per index, this is a thread local location, and thus we can do a regular load and store without any worries of races. And here, if we knew we were always going to the same location and we had a reduce available, we could do a corresponding reduction to compute the end result. Now, what's really cool is this works not just for CUDA in C++, but it works for CUDA and also AMD on any language that goes down to the LLVM level. So for example, here we have the Julia version of this. So there's a CUDA.jo bindings for CUDA where we can say create some shared memory in this kernel function, and then we can similarly differentiate that function and then compute the derivative now in a completely separate language. We've now demonstrated how we can use this to differentiate GPU code, and specifically in a variety of languages, but there's still one thing that we haven't talked about, which is maintaining correctness in the context of immutable or read-write memory. Now, let's take a look at this code here on the right. We say that the output at some given index equals x squared at some given index. We subsequently set that x to equal to 0. Now, the way we would compute the derivative here, the derivative of x squared is simply 2x. So we would say, the gradient equals 2x times whatever we need to propagate it by. However, we have a problem. This x of I is not equivalent to the same value that we used to compute up here because it was overwritten to set to equal to 0. As a consequence, what we might need to do is actually cache the value of x we used to do that computation in the forward pass, and then use precisely that value in the reverse pass. So what this demonstrates is that for correctness, Enzyme may need to cache values in order to compute the gradient. Now, Enzyme piggybacks on top of LLVM and elsewhere to be able to try to minimize the number of values. So for instance, if it can show by alias analysis or right type of properties that this value isn't overwritten, it'll avoid making unnecessary caches. However, this still may need to happen for various types of programs. And the complexity of GPU memory means that if you have a large cache, this can end up slowing down your program by several orders of magnitude because these caches tend to have to be inside of global memory, which also, if it gets too large, it might not even fit on your GPU at all. Now, for that original CPU case with the bar chart that I showed earlier, existing optimizations are sufficient to reduce this overhead that you get the good performance characteristics that you saw earlier. Also, notably, this has to happen for any 8E tool, not just Enzyme. Unlike the CPU case, however, those existing optimizations aren't sufficient. And what we did to remedy this problem is we introduced novel optimizations that speed up GPU code, and thus you can even use on the context that has nothing to do with differentiation, as well as introducing new differentiation-specific optimizations. And these new optimizations can speed up your program by several orders of magnitude.
So one quick question, William, is this sort of related to checkpointing, or is it similar to checkpointing?
It's related to checkpointing in the sense that this problem creates the issue, which then checkpointing partially addresses.
Okay.
So this issue is that you need certain values for your reverse pass, which can be overwritten. Checkpointing dives into this problem specifically to say, okay, how can we minimize this in the context of iterated for loops? And people say, okay, you can preserve at the middle point.
Oh, I see. Okay.
And so on. So it helps remedy it, but this is the overall problem it solves, if that makes sense.
Cool. Thanks.
Cool. So let's do one example of these optimizations now purely in an AD context. So say we have here this for loop that takes two vectors x and y. We sum up the value and we use that value in some function call or some instruction, don't really care what. Eventually x and y are overwritten. And now when we compute the gradient, we have the gradient of whatever that overwrite function was. And then we have the reversal of that for loop and the reversal of that use. Now, to compute the gradient of the use function, we need that original sum to be able to compute it. And thus, we need that sum rematerialized in some sense here in the reverse pass. Now, the naive thing that you can do is you can say, okay, x and y were both overwritten. So for all values that are overwritten that I might eventually need, cache them. And thus we can rematerialize our sum variable here by just loading from our caches of x and y and then computing the gradient of that use. However, we can think a little bit more cleverly and look at the computation or the use graph. So here I've marked in red the two variables x and y that are overwritten, and I have arrows showing how these different variables are used. So in this case, x and y are only used by the blue variable here, sum, which itself is required for the reverse pass, but not overwritten. So you could do now a minimum cut on this graph to figure out what's the minimum number of values you need to preserve to compute all of these values you need in the reverse pass, which is a fancy way of saying rather than caching x and y individually, since they are not individually needed, we can simply cache the sum variable and then use that cache in the reverse pass. And this generalizes to more complex things by using that graph view of the algorithm. One example optimization that isn't specific to AD, but instead specific to GPUs and comes up a lot in this context is that allocations and moreover any calls on the GPU tend to be relatively expensive. So suppose you had some function that had allocation for var1 and allocation for var2. We used those variables, then we deleted those variables. Since we can prove that these two allocations are in the same scope, rather than doing two individual allocations, we can simply do one combined allocation of the size of both of these, in this case, n plus m, setting the second allocation to some offset from the first. And thus, we've reduced the number of allocations in this sample code by a factor of 2, which for this type of code can reduce the overhead and thus the runtime of it also by a factor of 2. And optimizations like this one are beneficial, again, not just for AD, but practically any GPU program. We've written a whole host of these optimizations, and if you're interested in more details on them, please see our recent paper at Supercomputing. We have a variety of AD-specific optimizations and GPU-specific optimizations. We can now take a quick look at how this works in practice. Since we presented this work at Supercomputing, we had a large suite of, in this case, scientific benchmarks. So the specific benchmarks that we care about here is a discontinuous Galerkin kernel, this time written in Julia, and in fact, both for AMD and for NVIDIA. We have a lattice-Boltzmann method, which is a fluid dynamics solver. We have the LLVM hydrodynamics solver out of Lawrence Livermore, and both XS bench and RS bench, which are examples of this Monte Carlo algorithm that are respectively memory bound and compute bound. And then we go ahead and we compute the derivative of all of the inputs for these given programs with respect to the output. And for some of these code bases, these are several millions of inputs that we're computing in a single call. So what we have plotted here on the right is you can imagine first running your original program. That's often referred to as the forward pass. And then we also have a version where you can run it, which not just computes the original outputs, but computes the original outputs and the derivative of the sometimes millions of input variables. And this number right here is the overhead of the original computation and the derivative of all inputs divided by just the original runtime of the program. And all of these work relatively efficiently. And I sort of discussed before, automatic differentiation allows you to get the derivative of all of these inputs in a single call. And that's why they remain roughly a similar performance behavior to your original program. Now, there's one case here that you might notice, which is a little bit larger than the others. And it turns out that CUDA's memory, our register allocator, actually has a bug that the discontinuous Galerkin kernel here happened to hit, which didn't do a good register allocation. It turns out actually if we ran this on the AMD case, it didn't have that bug and other cases didn't have the bug. So hopefully someone here can go fix the bug and then this should be equivalently efficient. However, the story here that is worth telling is not these overall overheads, but it's really about how much optimization truly matters for doing differentiation. So it's more interesting here to talk about a graph that will look like this. So again, a bit of explanation here to what's happening. We take those same 6 tests from before, plot it on a different row, and we do the same sort of overhead computation where we say here on the left, the forward pass alone is a 1x overhead, and this is a log plot, so this is a 10x overhead, 100x, 1000x, etc. So first, we emulate what a existing tool would do if it could work. And again, remember, there is no tool presently that's able to differentiate GPU kernels. So this is running with Enzyme first prior to any optimizations on the LLVM level. And it turns out that 5 out of the 6 cases here instantly exhaust the amount of GPU memory and thus can't run. One of them can, and it runs at a 3000x overhead, which, I mean, it technically runs, so it's better than nothing. We then apply the first round of existing LLVM optimizations, just like we did for the CPU bar chart that I showed earlier. And this allows more of these programs to run. So for instance, now we get the DG kernel on CUDA that's able to run, the RS bench and XS bench kernels are able to run, but the overheads still aren't great. So for, say, the DG kernel, it's 1000x overhead, RS bench 6000x overhead, 26x overhead for XS bench, which is okay. And LLUS, it ran before, now it's able to get to a 2.4. Now we apply all of those AD specific and GPU specific optimizations, such as the ones earlier where we did the minimization of using the min cut of the number of values we need to cache, or the GPU allocation merging we talked about as a pure GPU case, and that reduces the overhead of these programs down to the runtime that we saw earlier, and also enables the rest of the programs, in this case, DG on AMD and LLVM, to successfully run. So the real takeaway from this here is to say that running automatic differentiation on existing GPU kernels is really intractable without being able to have optimization that interplays with it. Overall, Enzyme is a tool that's able to perform reverse mode and now also forward mode automatic differentiation of statically analyzable LLVM IR. By working on the LLVM level, we're able to get a couple of key benefits. First of all, we're able to differentiate code in your choice of a variety of languages, including code that uses multiple of these languages. Specifically, if you're able to differentiate after optimization, you're able to get a substantial speedup above existing tools that must differentiate before optimization. On the GPU case, this is a 4.2x speedup. And this is enabling it to get state-of-the-art performance with those existing tools. Moreover, we're also now the first AD tool that's able to perform general reverse mode AD for GPUs. And specifically, by taking those optimizations and building new ones for both AD and the GPU, we're able to improve this time to performance by several orders of magnitude. All of this is open source. You can visit Enzyme on mit.edu, see all the code on GitHub, join our mailing list or our weekly development meetings. And we have ongoing support for CPU parallelism. So we actually currently even have support for OpenMP and MPI and higher examples like Julia threads and so on, as well as forward mode. And we're working now on mixed mode and some interesting questions that come up in a memory context. This work was supported by a variety of different places. So first of all, there's a number of folks that I'd like to thank for looking at versions of either the code, trying it out, looking at slides, papers, etc. I personally was supported by a grant from the Department of Energy, and other colleagues were also supported by various other places within the Department of Energy, within DARPA, the German Research Council, and also the Air Force. Thank you so much. Any questions?
Great, thank you, William, for talk. We have time for questions from the audience. While we're waiting, I have one question about compile time. How does this impact compile time when you do AD, right, for LLVM parsers?
Sure. So, for example, on the GPU example, we computed the overhead of the compile time of the differentiated code versus the compile time of the non-differentiated code. Mm-hmm. And as you would expect, since we're generating potentially 2 or 3 more functions, the compile time was up to 2 or 3 times as long, but it's not the same order as the
so it's a linear increase. It's essentially a linear increase, basically, not more than linear.
Yeah, and that's basically because if we're generating more functions, we need to run more things.
Cool. All right, thanks. So are there any other questions from the audience?
Also, I apologize. I don't see a chat, so if you have a question, feel free to just chime in.
Yeah, there's a chat channel, I think. As well.
I did have a question I was wondering about. So you talked a little bit about how you could support differentiation across barriers in the context of kernels. I was just curious, does the way that you do it require that barriers be textually aligned, or could you support languages that don't impose that restriction?
Just to confirm, when you say barriers, do you mean language barriers or do you mean synchronization barriers?
I mean the sync threads barriers.
Yeah, so in this sense, the support for the synchronization barriers actually generalizes even past what we show here in subsequent work. If you have any type of parallelism that you can represent as, in some sense, a DAG, which almost all parallelism you can, so long as you reverse the parallelism DAG in the reverse pass, you will maintain correctness. In this case, the synchronization is one way to sort of create elements of that, where you say, okay, all of these things have to be computed before the thing goes past it. So even if it's not in the same lexical scope, etc., any way that you can build up a computation with that sync threads will be reversed by doing this corresponding reversal and putting the sync in that place, as well as similar mechanisms for generic tasks, if that answers the question.
Yeah, so I think what you're saying is that as long as you can tell what happens before what, regardless of what the synchronization primitive is at the language level, you can work with that.
I guess perhaps clarifying a little bit, you don't need to actually tell what happens before whatever else.
You just need to reverse.
In the sense that you just need to, you need to reverse.
I see what you're saying. Yeah, okay, that makes sense. Thanks.
So I think in CUDA 9.0 or later, I think maybe it was after CUDA 9.0, there was a change in our programming model for barriers where we think the short question for William is that volatiles. So if you have volatile accesses before, that is using flag to signal between threads in a warp, or how do you handle that? Does volatile have a special meaning to AD in your setting?
Sure. So the proof that we showed here for ease takes into context a original race-free program, and typically when you have some sort of volatile access that'll look like either a specific way that you resolve the races, or alternatively, a sort of atomic increment equivalent. You can reverse these. The way for doing so is slightly more complex. In essence, if you have ambiguity in your original program, you need to make sure that you propagate the value to wherever it actually came from. An example of this, for instance, that we demonstrate with MPI, unfortunately not in the slide deck, effectively involves storing where the non-determinism resolves to in your original pass, so you can emulate the equivalent non-determinism in the reverse pass. Other examples of non-determinism, you don't actually need to do that, but it is handleable, but it may be slightly more complex.
Okay. Yeah. Right. Okay, if there are no more questions, we can stop here. And thanks again, William, for great talk. Thanks for attending. Okay, bye.
Bye.